All right, so it's a pleasure to have Kristin DeVleming today, who will tell us about wall crossing for moduli of varieties. Please, go ahead.
Thank you. Thank you for the invitation. These have been great talks so far, and I'm happy to share some things that I've been thinking about and others have been thinking about. In the spirit of the sort of past talks that I've gone to, I wanted to survey a couple of results on moduli spaces and talk about a couple of applications or work in progress or various things that people are currently thinking about or people I know are currently thinking about in the world of wall crossing. So if there are any questions, anyone, don't hesitate to chime in. Part of this will be a little bit of a recap, and then part will be, more modern or more recent results or in progress works. So, okay, now I just have to figure out. Oh no. Hold on. There we go. I just have to, sorry, there we go. Now we're clicking. Okay. So I was gonna just briefly recap the several theorems on existence of moduli spaces of certain varieties, talk about what we mean by a wall crossing framework, and then discuss, as I said, mostly focus on some applications that people are thinking about and working on. So I think several things I will state won't necessarily be state of the art. They might be simplified versions of some of the main theorems, but to get a general idea of what's going on, I figured it was easy to state things in a way that was a little bit simpler. So if you have questions on anything or a generalization, please let me know. But throughout, as the usual disclaimer, I'm only going to be considering projective varieties over the complex numbers. And the first example that we will talk about with moduli of varieties will be KSB moduli spaces. So looking at stable varieties, and for those, I think almost everyone in this audience knows what I'm talking about, but if not, I'm looking at SLC varieties with ample canonical divisor and families satisfying Kolar condition, namely that the reflexive powers of the canonical commute with base change. So for example, for any grad students that are hanging out in the audience, the usual examples we look at are maybe genus at least two curves, or mildly singular hypersurfaces of sufficiently large degree in projective space. Since we're at a conference this week, I know that there will be some talks on, and there have been some talks on surfaces of general type, I should say surfaces of general type with fixed genus and irregularity. But the idea is fix some numerical invariance, kind of fix the objects you're parameterizing and try to construct a moduli space. And then the theorem, which is in Kolar's book now, for any dimension n and volume v, we have a Deligne-Mumford stack and a projective coarse moduli space parameterizing the SLC varieties of this dimension with ample canonical and canonical volume equal to v. I didn't state this theorem carefully about what families the stack parameterizes. This is just stating what objects it parameterizes, but there is more details that can be added. And a lot of my work has focused on explicit moduli. So this is a good point to point out that when you go to n greater than 1, there are very few complete descriptions of these moduli spaces. So moduli of varieties of dimension 2 or higher. By complete description, I mean, fix an n and a v and tell me everything that this moduli space parameterizes explicitly. There are many partial results for different classes of objects, but to the best of my knowledge, with a literature search, please feel free to add to this list if you have more. The completely described KSB moduli spaces of canonically polarized varieties include stable curves, genus G curves. This is an example of this framework. Work on surfaces that are quotients or covers of products of high genus curves. So there's several different papers, Van Opstal, Wenfei Liu, and Sonka-Rolenske, which discuss the various cases, products of curves, quotients of products of curves, and covers of products of curves. I may have said that out of order, but have gotten a complete description of everything that's parameterized by the moduli space, the KSB moduli space, including all the surfaces that are on the boundary. And then work of Alexeyev and Pardini studies Campidelli and Bernat surfaces, which are double covers of P2 and del Pezzo of degree 6 branched over certain configurations. So there, as I said, are quite a few partial results on different boundary components, a different component, like one small part of the singular surfaces that are parameterized by the KSB moduli, but I think these are the ones that are the few cases that we have a complete description. And I mention that now because we'll kind of come back to this point later in the talk. Once you have moduli spaces of varieties, though, we have seen that there's a natural generalization to moduli of pairs. So this theory of KSB moduli has an extension to the case of pairs. And I, again, was a little bit sloppy. I said for any NV and fixed marking of the divisor. So you have to fix something about the coefficients of the divisor to get a well-behaved moduli theory. And you also have to put various hypotheses on divisors behaving well in families. But if you imagine saying all of your divisors are some multiple of some fixed Z divisor, think of that as the fixed marking, there exists, so I suppose the marking should be in the data of the stack, but there exists a Deligne-Mumford stack and its projective coarse space, parameterizing now SLC pairs instead of just SLC varieties. And this has been studied. There's been quite a lot of work in this. There are more complete explicit examples known in this case, especially when the divisor D is a very, very small coefficient of something else. So Alexeyev's abelian surfaces, hacking moduli of plane curves, and many other follow-up work. There's a huge body of literature in this area, particularly focusing on the case of pairs. And yeah, there's much more that can be said, but we have, in some cases, we have or in some sense, right, we have a well-behaved moduli space of canonically polarized varieties and log canonically polarized pairs, and we can study them. We don't have a whole lot of traction on explicit examples in higher dimension, but there are still things that we have this well-behaved framework for. And now, I guess, there's been several talks on the Fano case. So I'll do a little recap of what is known in the Fano case. So K moduli spaces, we have, yes, I think Zishuan, Chuanyang, and Vanya all talked about K moduli spaces, but the notion for Fano varieties and the idea of moduli for Fano varieties is a little bit more nuanced. It's not just a singularity condition. We want to consider K semi or polystable Fano varieties. The K semi polystability condition does imply it's KLT. So you can think of a Fano variety meaning KLT with minus KX ample, and then the K semi polystability is an extra stability condition that not every Fano, not even every smooth Fano manifold satisfies. So for example, PN is a K polystable Fano variety, so we can make moduli of PN. But for just to give you a little bit of an idea of what this looks like for smooth Del Pezzo surfaces, we can completely determine the K semi or polystability. So P2, P1 cross P1, or Del Pezzo of degree 6 are K semi-stable. The blow-up of P2 at 1 point, or Del Pezzo of degree 7 are unstable. And first degree at most 5, they're K stable. So in all of these cases, we can put on, yeah, we can use K semi polystability where this is going to construct a moduli space. And if you've never seen K stability before, which I think again for this audience most people have, the Fano variety is K polystable if and only if it admits a Kähler-Einstein metric. So there is some differential geometric input into thinking about these varieties, but not every even smooth Del Pezzo surface is K stable. Or excuse me, some of them are K unstable. But nonetheless, with this notion, we can construct well-behaved moduli spaces of these objects. So if you fix the dimension and volume, so this theorem is, I guess, in Chuanyang's K stability book. It's due to many, many people, similar to the KSB theorem. But for any fixed dimension and volume, there exists a finite type Artin-stack and projective good moduli space parameterizing K semi and polystable Fano varieties X with ample anti-canonical divisor and anti-canonical volume equal to V. So this is, this theorem was actually, I guess, kind of completed quite recently, but even in, the time that this was being proved in sort of completion, there has been a huge body of work on K-moduli spaces. So let's review a little bit of that. First, in Odaka's body sun, there are complete descriptions of the K-moduli spaces for smooth Del Pezzo surfaces. So by this, I mean if you fix the volume and dimension 2, of your Del Pezzo surface, and you look at the component of the K-moduli space that compactifies the smooth locus, so the irreducible component that the smooth locus lies on for each fixed class of Del Pezzo surfaces, Odaka's body sun went through and described everything in these moduli spaces, including everything that's on the boundary, usually with some sort of GIT description. So we have complete descriptions of K-moduli spaces essentially in the dimension 2 case for the, quote, main component of the moduli space, the component that compactifies the smooth locus. And this is a rough estimation, so Vanya can correct me if it's wrong, but we have for at least families of Fano threefolds for which the K-moduli space is non-empty. You're shaking your head. You're muted.
Okay, around maybe half Moduli just points. Yeah, like
yeah, exactly. So I mean,
yeah. So yeah, that's maybe yes. Yeah, maybe yes.
So the part Vanya's pointing out, I'm cheating a little bit in saying this, but for the families of Fano threefolds of all of the different deformation types of families of smooth Fano threefolds, for the ones which the K-moduli space is not empty, yes, many of their K-moduli spaces are just a point. So we do have a complete description because it's one point. But we do have interesting complete descriptions for other families of Fano threefolds, namely ones whose K-moduli space is a one-dimensional and ones whose a certain few other examples that I'll mention later. But I think what I'm trying to indicate by saying this is that there is somehow K-stability, while being this slightly different notion, has relations to often a GIT or some other description. And so many people have been able to take some particular family of Fano threefolds and just write down the entire K-moduli. I'm not claiming this is easy, but there's sort of a way to start approaching this problem that is often intractable in the general type case. So K-moduli spaces, we have a little bit more known, or maybe a few more examples of explicit moduli spaces that are known. And then we also have an extension to pairs. So for any volume and dimension, and here I'm going to say the divisor has to be a Q divisor. So I said fixed rational marking, but imagine I'm just fixing the coefficients of the divisor to be rational numbers. Again, you can generalize these in certain ways, but let's say this for now, there exists your same art and stack and good moduli space parameterizing K poly and semi and polystable pairs. There's also been quite a lot of literature studying these. So what I'd like to focus on for the majority of the talk is sort of a prototype example to inspire what we mean by wall crossing. If you suppose that X is a Fano variety, maybe you can think of X as a smooth Fano variety, a smooth manifold now. It could be mildly singular, and D an ample divisor in some anti-canonical linear system. Then we could construct different moduli spaces of pairs based on different coefficients of the divisor. I think I changed, yeah, okay. I changed this so it was a little easier to state. But if you consider the pair X, C, D, and you look at its log canonical divisor, KX plus CD, depending on the relationship of C and R, you fall in these three different cases. Either you have a log Fano pair, C is less than R, you have we can call it trivial, at least numerically trivial, if C is equal to R, or an ample, kind of a log canonically polarized pair if C is greater than R. I'm implicitly assuming R is less than 1 in this, but if R is greater than 1, some of the things I will say will just be empty. Okay. But once you have this data, for each fixed C, you can construct moduli spaces of these pairs. So, and stacks. So I'm just writing down what points are parameterized by the stack. you do have to talk about families, and you have to be careful about what families of objects you have. But you can use the previous results to construct moduli stacks of these pairs where you have fixed the volume and dimension to be whatever the dimension of X is and whatever the volume of KX plus CD is, and use the theory of KSBA moduli to compactify if the coefficient is greater than R, or the theory of K moduli to compactify if the coefficient is less than R. And you can do this for each C. So no matter, well, at least for each rational coefficient for the K moduli side, although there is recent work of Yuchen Liu and Chu Zhao, who is doing this for R coefficients instead. But nonetheless, maybe assume C is rational in what I'm saying, so you don't have to worry about these issues. This is some moduli space that you construct for each coefficient, and it's natural to ask, I think, the following question: how do these stacks and their associated moduli spaces vary as this C varies? Also, what happens if C equals R? Sort of a separate question, but can you can construct these moduli spaces for any rational number, but that doesn't seem like it would be incredibly useful unless the moduli spaces sort of fit together in some family of moduli spaces. So just to motivate us, we're going to come back to this example. Think about first the case that X is P2 and D is a degree 4 plane curve. In this case, this is just like a simple example that we can start with. You can explicitly describe what these moduli spaces are for each coefficient. So I'm going to put a picture. It's going to probably be very small depending on what screen you're looking at. But along the bottom of the picture is a chunk of a number line that goes from 1 to 0. So 1 is on the left and 0 is on the right. And I've put a moduli space roughly on top of various numbers, indicating some general behavior. So if you do this construction of these moduli spaces for small coefficient, so when you're on the right side close to 0, if your coefficient is between 3/8 and 0 and 3/8, you get one moduli space that's always isomorphic to the GIT compactification. Something happens at 3/8 if your coefficient of your divisor happens to be between 3/8 and 3/4, you get a different moduli space. It's something else. And then when your coefficient is 3/4, you get yet a different moduli space, which I haven't told you how to construct, but maybe believe me at the moment that you get something there. And you can continue. When your coefficient is between 3/4 and 5/6, you get a different moduli space. And when your coefficient is between 5/6 and 1, you get yet another moduli space. So just looking at this picture, sort of suggestively, there seem to be finitely many values where the moduli spaces were getting change, and there seems to be some sort of openness. There's C that the moduli spaces agree for C in some range. And that is going to be the content of the next several theorems about wall crossing. So I will start, I think, with the K moduli wall crossing, but to introduce some terminology, I guess we don't have a theorem yet, so we don't know that these words are sort of well defined, but the values of C for which the moduli spaces exhibit a change will be called walls, and a description of the change in the moduli space as you go from a wall, maybe C naught plus epsilon to C naught minus epsilon, as you cross a wall C naught, are called the wall crossings. That's what we'll say. And the goal, I think, of many people that do this is to understand these wall crossings. Where do they come from? Can we describe them? How many are there? What applications do they have? So I'll give 3 results on wall crossing in each of the sort of 3 cases. And this prototype example is what we're thinking of. So maybe I should click back. The prototype example we're thinking of is X is a Fano variety and D an divisor in some multiple of the anti-canonical linear system. That's the case I'm going to state these theorems. They do generalize slightly, but I'm going to state them just in this case for the purposes of this talk. So in this prototypical example, in the log Fano case, work of myself, Kenny Asher, and Yuchen Liu, and follow-up work of Chu Yu says that you can make the K moduli space for each of these different coefficients, and they exhibit the kind of, quote, expected wall crossing structure. There's a finite sequence of rational numbers where the stability conditions change. And as long as you're in the interior of one of these intervals between the walls, so if you're between C1 and C2, the moduli spaces are isomorphic. Their stacks are isomorphic, in fact. And at the wall, you have a precise understanding of the wall crossing. So the stacks MCI plus epsilon and MCI minus epsilon actually admit open immersions into the K moduli stack at CI. And these open immersions descend to projective morphisms on the K moduli spaces. So you then, if you're handed one of these problems where you're trying to compute moduli of X comma CD, you could imagine trying to vary C from 0 to R and then see what different moduli spaces you get. And I think I mentioned this some cases a little bit ago, but this theorem does generalize to the case of multiple divisors. So instead of just saying X is Fano and D is one multiple of the anticanonical system, you can have multiple divisors D with a coefficient vector, and then you get sort of you get a polyhedral, you get a decomposition of the coefficient domain into this polyhedral wall and chamber structure. And Yuchen and Xiu recently have some papers out that extend this to the non-proportional case where your walls don't have to be at rational numbers, so they have to develop the theory of R divisors, or the theory of kind of K stability or K moduli when you have real coefficients instead of Q coefficients. But you can do wall crossing for K moduli, is what this says. And on the other side of the picture, so this is work of Kenny Asher, Dori Bellary, Giovanni Chiostro, and Joel Petafalvi, and then follow-up work of Fenjun Meng and Zhisheng Zhang for the KSBA case in the log canonically polarized case. I guess I use the same subscripts. These CIs are different than the other CIs, but that's what I get for making slides. There is a finite sequence, again, of rational numbers where the stability conditions change. And you have something similar, but not exactly the same. So as long as you're in the interior of one of these intervals, your stacks are indeed isomorphic, and you get morphisms of the KSBA moduli stacks, but you don't necessarily have open immersions anymore. And the morphisms descend to projective morphisms, but the right arrow, the one from MCI minus epsilon to MCI, is an isomorphism, at least up to normalization of the stacks, or of the spaces. So in fact, there's something much stronger here. You can have you can imagine you get a morphism on the moduli spaces up to normalization from any coefficient to any smaller coefficient. And again, they prove this they have a more general result in case of multiple divisors with a coefficient vector, and the case where X, I said the non-proportional case, so D is not a multiple of K, but also like X doesn't have to be Fano for this to be true. You can pick any XD where KX plus D is ample and apply this framework. So we have some idea, given any pair, if X happens to be Fano, XCD, at least when you're in the log Fano range and the log canonically polarized range, you have these wall crossing morphisms. And then at least in certain cases, we're working on some things in general, but at least in certain cases, there is also a quote wall crossing at the canonically sort of the K trivial range, the KX plus RD equaling 0 case. So I'm only this is work of myself, Kenny, Dori, Harold, Giovanni, Yuchen, Xiaowei Wang, and then follow-up work of Harold and Yuchen that says if you want to consider all pairs, maybe X comma RD. So here I'm thinking about X being Fano still. That's not a hypothesis, but that should be, such that KX plus RD is trivial. There exists an Artin stack locally a finite type parameterizing these pairs. And in fact, it is S complete, it's theta reductive. It has all of these good properties to admit a good moduli space, although it doesn't admit a good moduli space in general. In dimension 2, it does. So if you imagine that the dimension of your X is 2, you can say that you have an actual wall crossing on the entire picture. So when you cross from the log Fano range to the general type range, you get this wall crossing. You have the kind of largest K moduli space, K moduli stack injecting into the Calabi-Yau stack, or quote Calabi-Yau. Here, I just mean it's an SLC pair with trivial log canonical divisor. And then you have an open immersion from the sort of smallest KSBA moduli space into that as well. And on at least the quote main component, so typically we're thinking about one fixed, this is for the dimension 2 case, right? So by main component, I'm thinking about the component that parameterizes smooth Del Pezzo surface with the appropriate divisor. But this open immersion that you get in general actually descends to projective morphisms on the moduli spaces that you can construct in each case. So I didn't define what an asymptotically good moduli space is, but here the quote asymptotically good moduli space is just like proj of the canonical ring of the Hodge bundle on each side of the moduli space. So this is those are 3 wall crossing results, but just to ground us a little bit, because those are 3 sort of abstract statements, back to the example of a degree 4 plane curve, it just says that we can kind of knit this picture together. So this is the same picture. Again, if you're looking on a small screen, it will be very small. But as you take the coefficient of the plane curve from 0 up to 1, you get 5 different moduli spaces. You have, if you start on the, I guess the left side where the coefficient is 1, you have the moduli space of genus 3 curves, M3 bar, which the notation is not great, I apologize. So M3 bar equals M1 minus epsilon, but here M1 minus epsilon means the moduli space of pairs x comma 1 minus epsilon d. So x is a surface and d is a curve. Work of Hassett proves that these are equal. And as you vary C, as you start to decrease C down to 0, you get this very explicitly described wall crossing framework. So when you cross the wall at C equals 5/6, you get a morphism to the next moduli space. When you cross the wall at C equals 3/4, this is this kind of Calabi-Yau wall, you get a flip on the moduli spaces. And when you cross the wall at 3/8, you get another contraction of the moduli spaces. And so, I mean, this is a very special example, but the theorems are trying to indicate that this is the typical behavior. As your coefficient ranges from 0 up to kind of the log Fano threshold, you get a finite number of K moduli spaces that you can describe, hopefully. And when your coefficient ranges from the log Fano threshold up into 1, you get a finite number of KSBA moduli spaces. So this is the maybe typical kind of pattern to keep in mind. And what I would like to do in my second half of my talk is discuss why. Why are we doing these? Why does wall crossing, other than maybe being interesting, what does it help us do? Does it help us answer other questions, or what are people, all the authors I mentioned, what are some of us doing now? I don't have any questions so far. Well, let's discuss a few different applications. Some of these I will say a lot about, some of them I will say a little. It depends on how familiar I am with the specific work that is being mentioned. But all of them come specifically from the idea that wall crossing, as we saw in the previous picture, allows us to interpolate between different moduli problems. It allows us to, like, in this case, we took M3 bar, and which was one moduli problem, genus 3 curves. We took a different moduli problem, the GIT of quartic plane curves. And in fact, the M sub 3/4 is, in this case, it's actually a Bailey-Borel moduli space of K3s that are covers of P2, degree 4 covers of P2 branched along quartic. So there's many different interpretations of moduli spaces, or ways to construct compactifications of moduli spaces, and wall crossing gives us an opportunity to interpolate between these different spaces. So in the spirit of what we said at the beginning, the K moduli spaces tend to be simpler to describe completely. Notice the word simpler, not simple. These are not necessarily easy to describe, but they, at least we have some evidence that if somebody hands you a pretty friendly Fano variety, or maybe Fano threefold, we can just start attacking and writing down what the moduli space is. And also, I haven't proved anything I haven't stated a theorem to this effect, but for many different modular compactifications, like the GIT compactification or a Bailey-Borel compactification, for different coefficients, the moduli spaces of pairs we're getting coincide with other compactifications, or sometimes have a forgetful morphism to them, or vice versa. So they allow us to take some information from one moduli space and transport it to the next. So this is really the entire framework. We are using wall crossing to transport information from one moduli space to another. And then, as I said, I want to give you a couple examples of people who are like, I don't know, what some of us are doing. And the first example is not something that I am actively doing. The rest of them are. So I don't want to say too much about this, but this is a question I get asked in every talk that I give on wall crossing. An application to Chow and cohomology. So every time I give a talk on wall crossing, someone asks me, can you use this to compute the Chow ring of this moduli space, or vice versa? And usually my answer is no, but this is something that people can indeed do and have done in certain cases. So if you look at sextic plane curves, so the same picture I just wrote for quartics, except for a curve of degree 6 in P2, you can make these moduli spaces of pairs. So you can look at moduli spaces of pairs P2, small coefficient of a sextic, so on and so forth. And work of myself and Kenny and Yu-Chen relates this to existing work of Shah and Loenga, comparing the moduli space of these pairs to moduli spaces of degree 2 K3s. A generic degree 2 K3 surface is a double cover of P2 branched along a sextic. So what is known, there's a lot of equalities, so these are different theorems, but what is known is that if you look at the Bailey-Borel compactification, F2 star of degree 2 K3s, it is this M1/2, this boundary, this kind of Calabi-Yau moduli space of pairs of P2 and a sextic and their degenerations. This admits a Q factorialization to a particular compactification that Shah constructed, which I believe he called F star hat, which happens to be a K moduli space for the coefficient of the curve between 1/4 and 1/2. And then this admits a map to the GIT of sextic plane curves, which is a weighted blow-up of a triple conic. And this picture, it looks very similar to the quartic picture, but this picture was known well before the theory of K-stability, and Kirwan and Lee used this picture to compute the Betty numbers and the cohomology of this Shah compactification, this F star hat of degree 2 K3s. And then they were actually able to compute information just about F2, not just the compactification. So this works via wall crossing. So Kirwan, this weighted blow-up is the Kirwan partial desingularization of the GIT of plane curves. And the idea, there's a bullet point that says idea at the end, but the idea is roughly to keep track of what is appearing, right? You're getting, as you do these wall crossings, you're getting these different loci, right? These different subvarieties, maybe an exceptional divisor of the blow-up or a locus of a small contraction. And you keep track of what that parameterizes and look at, those cycles in the Chow ring or things like that. If you want to remove a cycle, look at some sort of interior, or remove some type of curve, then this will generate some relations in the ring, so on and so forth. So Kirwan and Lee computed essentially cohomology of the moduli space at the top of this page, the F star hat. But very recently, Samir Canning, Dragish Pran, Rahul Pandarapande used this same idea to compute the Chow ring and the cohomology ring of the moduli space of degree 2 K3s. So here I just put F2, not F2 star. This is just the interior, just the quasi-polarized K3s with mild singularities. And they used this wall crossing and the previous results of Kirwan and Lee to get a complete description of this A star of the Chow ring and the cohomology ring. I believe all this is with rational coefficients, but the computations are quite involved, but the method that both of these use suggests generalizations to other wall crossing pictures. You have to keep track of many more things, but at least Drago Shaprea thinks that this should be doable for hyperelliptic quartic K3s following the same method. And then just because some of the authors are in the audience, I'm at a conference now, and there'll be a talk tomorrow by work of Kenny Asher and Duncan Lee, who compute Chow and cohomology rings of other moduli spaces of plane curves. And I will let Duncan talk about this tomorrow if you're at my conference. If you're not, I'm sorry, you will have to ask them on your own. But it's a similar method. And so, as I said, the idea with all of these is use the explicit description of the wall crossing to determine what classes are added and understand the relations that are generated from removing different classes, particularly if you want to look at like F2 inside this F2 hat. And anyway, there's many more things you can say. This is just one example. This is the sextic plane curve example, but the method does suggest generalization to cases where there are a tractable number of walls. Some of these problems, have maybe 13, 14 wall crossings, and I think that's going to be a little bit too far. You're not going to be able to compute everything in a reasonable way. But this is one application that people are using this machinery for. So there's one. More applications. We'll go in a totally different direction. Instead of computing the Chow or cohomology, related direction, but instead of computing the Chow ring of a moduli space, we might ask to compute log canonical models of the moduli space. What happens when I run a particular minimal model program on the moduli space? So I'm trying to use a different letter because I already defined an M sub C. So here my math script M is just the usual moduli space or the moduli stack of genus G curves and of Deligne-Mumford stable curves. And what's now known as the Hasse-Keil program is to take the log canonical divisor on mg bar and on the stack, this kx plus alpha delta, where delta is just the boundary divisor on the stack where all the components are taken with coefficient 1, and run the MMP with respect to this. If I take proj of this ring, for any, it should say in here, for any alpha such that this divisor is big, does each of these varieties have a modular interpretation? Alpha, for G very large, the canonical divisor is big, so you don't have to worry about this. But for G small, at some point, you will hit a value of alpha where this divisor stops being big. So, but does each have a modular interpretation? And if so, what is it? And how can we understand it? Similarly, I didn't state this very precisely, and not everyone, I think, calls it this, but at least in some papers, this is maybe the Hasse-Keil-Olenga program, which is doing something very similar, but on the Bailey-Burrell compactification, or on some sort of, compactification of some, in this case, I want to think about this as a maybe Bailey-Burrell compactification of K3s or something else, but let's say of K3 surfaces, and then the HIs are appropriate Heegner divisors. So Loenga worked out several different Q factorializations of Bailey-Burrell moduli spaces based on Q factorializing some of these Heegner divisors that appear. So I'll revisit this a little bit more explicitly in a moment. But a priori, right, we're taking some projective variety, mg bar or the Bailey-Burrell compactification, and we are just running a minimal model program that doesn't necessarily have to have anything to do with another modular compactification, but the examples we have suggest that perhaps it does. And wall crossing, gives you another version of understanding these objects. So following work of Hassett, what Kenny and Yuchen and I were able to prove was that for quartic plane curves, the picture for wall crossing of quartics that I already did exactly coincides with the Hassett-Keil program for M3 bar. So despite being defined in very different ways, these moduli of pairs that we get coincide exactly with the walls that you get in the Hasse-Keil program. Similarly, with Xiaowei Wang, we can do the Hasse-Keil program in genus 4. And It says complete the hasn't kill program. Really, this just means find all the walls and say what's happening at each point, which provides a modular interpretation of each moduli space, M4 bar alpha. And then back to the Loenga program, for degree 4 K3 surfaces, we can actually, there are two, or if you look at degree 4 K3s, there's two natural Heegner divisors. One is the divisor parameterizing hyperelliptic K3s, and the other is the divisor parameterizing the elliptically fibered K3s. And if you run this program, so if you take the log canonical models of these, there was a typo in my definition. There should be a Hodge bundle. Sorry, I apologize. There should be a Hodge bundle here in the definition of this program. But nonetheless, if you take the models of the Hodge bundle plus A or B, like maybe A times the hyperelliptic divisor plus B times the elliptically fibered divisor here, this program interpolates in two-parameter family, actually, between the Bailey-Borel moduli space of quartic or degree 4 K3s and the GIT of quartic surfaces. So this actually ends up verifying several conjectures made of Laza and O'Grady, but all of these problems kind of work in the same way. So the main idea is we've constructed this completely separate, similar looking, right? But the separate moduli space, M sub C, depending on the problem. It might be moduli of pairs P2, comma C and a quartic, or it might be P3, comma C and a quartic surface. But if you can verify ampleness of the appropriate divisor on each of these spaces, then it is proj of that divisor. So you use uniqueness of log canonical models to prove that the moduli space pairs you get is in fact the moduli space that is being constructed as proj of this variety, which may or may not seem interesting, but something I want to point out about this is that part of the point of doing this for all of these cases, it gives an alternative perspective in these cases for the Bailey-Borel moduli space. In particular, it gives a stack, so it gives a universal description of it. So the Bailey-Borel, the compactification, F star, right, doesn't carry a universal family, but this gives you a different stack that is something, does have a universal family that has a good moduli space that is the Bailey-Borel. For degree 4 K3s, you have to take a particular Q factorialization to get this to be true on the nose, but this construction gives you a way to think of the Bailey-Borel as the good moduli space of a actual, family of objects. So it tells you what the boundary is supposed to be. And this is proven useful pretty focused, both the Chow and cohomology and this log canonical models, on kind of facts about the moduli space itself. It's the moduli space of varieties. But then I want to shift gears. Oh, my internet connection is unstable. Oh, it's back. Okay. I want to shift gears a little bit to say what wall crossing can say about the objects it's parameterizing. So this was brought up last time as well, but the last talk, in Vanya's talk, I guess. But one application of this is, for those of you in the room, it says explicit constructions of K moduli spaces at the top. For a fixed deformation family of smooth Fano threefolds, which are K poly semi-stable, this is a big work in progress. But then if a general member is K poly or semi-stable, can you describe the entire irreducible component of the K moduli space that parameterizes that object? So this is something that we can do in several cases. And the way one way it has successfully been done is with wall crossing. So how does wall crossing come into the picture? This doesn't always apply, but many of these Fanos, I don't know, occur as covers of other Fanos. So this is just an example. This is the first one that we did. Quartic double solids are double covers of P3 branched over a quartic, which means, and also with the input, that K semi-stability of X is the same as K semi-stability of, Y should be P3 and D should be S. And K semi-stability of a cover is equivalent to K-semi-divisibility of the base with the appropriate divisor. And so you can use, before I say you can use, some phanos are covers of other phanos. Others are hypersurfaces in Fano varieties. I'm not saying anything groundbreaking here. But the point is then this becomes a wall crossing problem, right? You study moduli of pairs, either moduli of pairs X, C, D, where X is the thing your Fano is a cover over, or X is the ambient space your Fano embeds in. And if you study moduli of these pairs, when you start with very small coefficient, typically you have some simpler moduli problem, and you try to increase the coefficient to where you want to go. Maybe for example, quartic double solids, you want to increase the coefficient from something very small up to 1/2. And then if you could successfully get to 1/2, then you have a complete description of that moduli problem, of that moduli space. So this has been employed successfully in several different examples. I don't think I have all of them cited, but I have a couple that are written down. So the quartic double solid case we did, we have a complete description for the moduli space of pairs compactifying the locus of P3 and 1/2 a quartic, which gives a complete description of the K-moduli space of quartic double solids, which I looked up, and in the Mori-Mukai classification, or the classification on phonography, this is 112, if I typed it right. We have to believe I didn't make a typo. But then there's many other examples, right? So Abba and Sheltov, Kaspersik, Liu, and Petracci did quartic surfaces, or not quite the complete moduli space, but construct a lot of degenerations of quartic surfaces in P4, quartic threefolds, sorry, quartic threefolds. And so we have something Fano, by thinking of them as pairs and doing wall crossing. Yichen and Zhenren Zhao did used wall crossing to study K-moduli of Fano family 215, which these numbers might mean nothing to you. You don't have to worry about it. Myself, Lena G, Patrick Kennedy Hunt, and Minghan Kwek used wall crossing to study the entire K-moduli space of family 218, and so on. I put ... There's more examples, and there's a lot of work in progress. But the idea is that wall crossing gives you a way, like this is part of the reason some of these K-moduli spaces are tractable. You can start with something and try to compute. But even if you don't have anywhere to start, for example, with my work with Lena and Patrick and Minghao in family 218, we wanted to say some K-moduli space was isomorphic to some GIT moduli space, and then you do wall crossings from that GIT. But then it turns out there were, the GIT had been incorrectly done, so we just threw it away and we just do the K-stability without the GIT. And it still seems somewhat tractable. So wall crossing gives you at least a framework to start computing some of these K-moduli spaces. And you can get several different explicit examples. In the other side of the picture, KSB moduli spaces, let's say for surfaces only, there's very few examples, as I pointed out already. You could try to use wall crossing for certain examples. Here's one that I've been thinking about with a few other people, and many other people are thinking about this. You have H and I surfaces, which are double covers of either P2 or the singular quadrate cone branched along a particular curve. And if you want to construct these KSB moduli spaces, this effectively leads you to studying moduli of pairs X 1/2 D. So if you want a surface that is a double cover of P2 branched along an octic, if I want to know when that's SLC, I should know when P2, 1/2 octic is SLC, and so on. So if you want to describe a complete KSB moduli space, and you happen to have something that has some additional structure, it's a double cover of something, it's a fibration over something, etc., you may be able to use this technique to sort of tackle it. And this is in progress. This is, at least for this specific example of H and I surfaces with Kenny and Yuchen, and also Julie Rana and Fei C, we were looking at K-moduli wall crossings for these particular pairs. Okay, I mean, this is the same thing we said before. K-moduli wall crossing for pairs with some particular divisor. Here, think of X as P2 or a degeneration, and D as an octic or a degeneration, and so on. And the K-moduli is quite easy to describe. So for both the H and I surfaces, we can completely describe all the K-moduli wall crossings. And then they use this theory of boundary polarized Glabiao for the coefficient, either 3/8 or 2/5 or whatever the coefficient that you have to do across here is. And then the interesting and more complicated part is now we want to get all the way up to 1/2. You start with some small coefficient C and you try to increase that coefficient up to 1/2. Once you get into the canonically polarized range, the wall crossings are much more involved. So say this is in progress. And they're not necessarily more involved computationally, but they're more involved in just sheer number. So for both the H and I surfaces case, there's at least 30 walls in the range from 3/8 to 1/2 or 2/5 to 1/2. There's just like, it's just sort of too many to write down. Like 3/8 to 1/2 is not that big of a range, but in progress. And nonetheless, you can construct degenerations of H and I surfaces that appear in these KSB moduli spaces with many, many components. So we have some degeneration of an H surface that has more than 30 components and a very particular, configured in a particular way. So wall crossing may, even a problem like this, which is maybe one of the simplest ones we can start with, might not get us all the way to 1/2 just because there are so many walls to pay attention to, but it will at least get us to describing surfaces, like interesting surfaces that are appearing on the boundary of this moduli problem that we were either maybe appearing in large codimension or small codimension that we didn't know before. So if you have an explicit problem, this is a way that you can kind of tackle at least writing down many things in the moduli space. And so as maybe a surprising consequence of like, also why are you writing down all these things in moduli spaces? It turns out that sometimes this tells you surprising results that a priori look unrelated. So I have maybe a few minutes left, so I'll say perhaps one more thing, and then maybe we'll end there. But a result that Kenny and Yu-Chen and I obtained when we looked at these moduli of quartic quartic K3 surfaces was it's a classification result. The only canonical Gorenstein degenerations of P3 are these four surfaces, or these four threefolds. P3 itself, the cone over a smooth quadric surface, and the cone over a singular quadric surface. That's what P1, 1, 2, 4 is. And a sort of mysterious threefold called XU. XU has one non-Q factorial singularity that is a weird thing, but we can tell you explicitly what XU is, but the point is there's one specific thing that appears. And this it's something that kind of appeared as a byproduct of our work, but if you look at a lot of the literature on P2, a lot of the random moduli problems and random things we've computed about moduli spaces of something that involves P2 requires a description of all of the KLT degenerations of P2. And we're far from that here. This is only the canonical degenerations, but it's only like there are very few canonical degenerations, so this was somewhat surprising. And it a priori, as I said, looks maybe unconnected to the theory of wall crossing, but the proof uses wall crossing. And the proof is the idea is if you had a canonical Gorenstein degeneration of P3, it has an anti-canonical section with mild singularities, has some dx anti-canonical section. And so it would appear in some pair using some tools from K-stability of x comma 1 minus epsilon d. So it appears in one of these moduli spaces for coefficient very close to 1. So if you can study all of the walls, which is what we did, and get a description of all of these moduli spaces, as a byproduct, you've computed these explicit replacements, and you've produced this very short list of canonical Gorenstein degenerations of P3. Similarly, if you would like, you can find other interesting degenerations of P3 via wall crossing for higher degree surfaces, maybe like quintics or etc. These have worse singularities, these are KLT, but you can still construct other interesting degenerations. And this seems like something that if you happen to do one of these wall crossing problems, you can get these kind of interesting byproducts of that you weren't trying to get when you started the problem, but classification results on Fano varieties or whatever your ambient space that you're parameterizing is. So I only have a couple minutes left. I put one other thing on the slides, but it's very, I mean, maybe I'll just run through it quickly. This is something that's very much in progress that I've been working on with a couple other people. And I have no claim to say that this is actually going to give information, but wall crossing, oh, okay. Sorry, what about other phonos? Yeah, you could try to classify other generations of other phonos in this way. But maybe the last thing I'll say is that wall crossing seems to, as ever, right, turn some hard problems into other hard problems, which maybe are interactable in a different way, but still could be studied. So for a very precise question, right, this is an open question, does there exist a complete subvariety of MG of dimension G minus 2? So is there a, like, for M4, this is the first place that this is open, is there a complete surface inside M4? And here M4 is the locus of smooth genus 4 curves, not all genus 4 curves. This seems sort of, you know, like, this is a very hard question, but for genus, like, you can produce, maybe I'll say, for genus 3, this is not open, but you can produce some examples of complete curves in M3 via wall crossing. M3, so my boldface M3 is the moduli space of genus 3 curves, has, you know, it's birational to the GIT of quartic plane curves. And what you can prove, which this was already known, but if you want, you can prove this via wall crossing. If you had a complete curve in M3, it has to map to a complete curve in this GIT moduli space that only intersects the singular curves in the double conic. So maybe a precise way of phrasing this was, can you find a curve in the projective space of vortex in P2 that only intersects the discriminant divisor in the locus of double conics? We know these exist by the fact that we know there are complete curves in M3, but what are they? What are they? And so, you know, I have some work with a couple of people where we can produce some examples of these. They don't tell us anything new, but then I think the more interesting case, if, you know, depending on the methods, it's going to be a different projective space, but roughly for the genus 3 case, right, you've turned the question about complete subvarieties of M3 into an interpolation problem in projective space, right? This P, this P of H0 of 04 is just a P14. And you have the discriminant divisor, which is a degree 27 divisor, and you want to find a curve that intersects that in prescribed points. So it's turned this hard question into another hard question, but a very different question on interpolation. And for M4, if you just wanted to find complete curves or complete surfaces, you'd be looking at complete families of 2-3 complete intersections. And then, so one could try to ask, that only intersect the discriminant in sort of prescribed way, but like, what are these? And so that's open. I don't know what these are, right? But you can use wall crossing to translate, I guess, the hard problem about complete subvarieties of M4 to probably an equivalently hard problem about complete subvarieties of 2-3 complete intersections, but you know exactly where they have to intersect the discriminant. And so you turn it into a interpolation problem in the Hilbert scheme, which is kind of what it was to begin with, but it's just a precise way of phrasing it that at least tells you something for genus 3. This is very much in progress, and I'm not claiming that it will lead to, you know, interesting results for M4, but wall crossing, as many things in math, turns something hard that we don't know how to do into something else hard that we don't know how to do. So on that note, I will end. I say thank you for listening, and I'm happy to answer any questions you have.
Thanks so much. Questions for Kristin?
Can I have a small question?
Yeah.
Kristin, you mentioned P2 and the quartic curves and P2 and the sextic curves.
Yeah.
Did anyone did quintic curves?
We did quintics, yeah. So Yuchad and Kenny and I did quintics. It's just a lot more complicated. There's I don't know, 8 walls or something,
Okay.
and most of them are small. Most of them are flips, and so. But
so everything is known in this case, yeah.
The K moduli side is completely known. So the moduli space of pairs P2 like comma C quintic, where C is less than or equal to 3/5. It's completely known. And also 3/5 plus epsilon by work of hacking, it's known. But I think I don't remember the boundary that hacking ends at. But so there is some, if you want to go all the way up to 1, there's some range that's not known. And at some point, I knew a graduate student that was working on this, but I think they left academia. So I don't think any results in this way have been, out there.
Can I ask a question, Kristin?
Yeah.
You had this example where the chain of stability didn't give open immersion among the moduli stacks. Could you say what that is? And also the map that you said was the isomorphism up to normalization. Is that because you don't know that they're normal, or because you have example when they're not?
Yeah, there are examples where they're not normal. But so there are examples. I guess the theorem also this theorem of a bunch of people, but we're almost there. Okay, this is what happens when you make slides that have too many checks. Okay. Yeah, so these I guess the moduli spaces don't have to be normal. The stacks don't have they a priori have many components. So maybe you have some components being normal, but saying, right, I guess kind of the typical way to prove that some component of these things is normal is by doing some deformation theory and concluding maybe the stack is smooth, so the quotient is normal. But typically these stacks have the deformation theory is quite obstructed, right? So so there are examples where these moduli spaces are not normal. So you do have to take normalization in. Actually, I know example. I don't know. Yeah, there are various examples, but the here you have. So I guess the kind of part of the problem is you can have. So this is the canonically polarized case. So you have pairs you have SLC pairs x comma c plus epsilon d, and then you want to shrink that epsilon. And still have it be to say you have an inclusion, right? You'd want to shrink that epsilon and still have it be both SLC and ample, kx plus d is ample. And if those conditions are not true, then you don't get or similarly, if you have ci minus epsilon, you want to increase the coefficient so it's still SLC, which, the epsilon is sufficiently small, so you could do that. But also maintaining, just want to hear, do you have a good example where these are not?
Right. So I think the morphism you have to pass to normalization here. So I think the wall crossing morphism in this case, they are obtained by running relative MMP and taking the ample model. But those ample models are done on the family, so they don't necessarily restrict to the ample model on the central fiber.
Yeah.
So it can have 2 different components, and when you normalize, you're running MMPs on different families, and then when you restrict to the central fiber, you get different MMP sequence, and so they don't glue back together. So that's why you have to normalize everything to run those MMPs. I think I forgot the precise example. I think in the original paper by Kenny, Dory, Giovanni, and Joe, I think they had an example that maybe they attribute to Janos as well, that has this kind of phenomenon. So yeah.
Thank you.
Other comments or questions for Kristin? So if not, thanks again.
Thank you. Thank you for listening.